Hello all, my name is Justin Tyska and I'm a graduate student working with Dr. Dang in the space weather section of our physics department, and I'm going to be presenting a poster about the ionospheric disturbances generated by the 2015 Kabuko volcanic eruption. This is a comparison of simulations in the global ionosphere thermosphere model and global navigation satellite system observations. I also want to thank my co-authors Dr. Zhang and Dr. Lin for their support. It has been known for some time that explosive events can generate acoustic gravity waves that then propagate to high altitudes and influence the near-space plasma environment known as the ionosphere. We can measure these waves using the delay of GNSS signals to calculate a line-of-sight quantity known as the total electron content, or TEC. These plasma disturbances, when induced by volcanic eruptions, are termed covolcanic ionospheric disturbances, or CVIDs for short, and understanding the primary mechanisms that are relevant to explain the variety in waveform characteristics is still an important open question for the community. The motivation here is that we believe these data model comparisons can really be used to provide in-depth analysis of complex case studies to discern the relevant physics and improve both our models and understanding. The focus of this study is to simulate ionospheric total electron content variations induced by the first phase of the 2015 Kabuko event and compare these simulations to GNSS data while attempting to investigate different primary acoustic gravity wave forcing mechanisms. Moving on to the GNSS data for the event, Figure 2 shows the data derived for a few satellite receiver pairs. The black curves in the left panel show the detrended TEC data measured by the right axis and tech unit, while the background contour represents the spectral content of the signal measured by the left axis in millihertz. The x-axis shows the universal time, and the dashed line represents the time of the snapshot shown in the right panel. The right panel shows the estimated sub-ionospheric piercing point trajectories for the satellite receiver pairs, which roughly show how the distance and orientation of the measurements change with time. The three closest trajectories in the right-hand panel correspond to the top three data series shown in the left panel. So you can see there are multiple wave packets of high-frequency fast oscillations near the volcano representing acoustic waves, and then further away a lower frequency gravity mode starts to dominate the signal. Figure 3 below is just a reorganization using all the data such that we can determine the apparent phase speeds. This again really displays fast phase speed acoustic nature of the oscillations near the volcano and the low phase speed nature of the gravity oscillations far away from the volcano. We wanted to see if our numerical model of the IT system could reproduce this result, and for that we needed a simplified representation of the volcano as well as the propagation to the lower boundary of the global ionosphere thermosphere model. Here we represent the volcanic forcing as a broad spectrum with a dominant peak at the local acoustic cutoff frequency shown in figure 4, while the propagation of those waves to the lower thermosphere is done using spherical waves where two propagation mechanisms are tested. The direct propagation assumes waves propagate directly to the boundary, while the ground-coupled propagation makes assumptions on the horizontal phase speed dependent on waves traveling downward from the source. Finally, the complicated dynamics and interactions of the ionosphere-thermosphere is calculated using the global ionosphere-thermosphere model, which self-consistently solves the Navier-Stokes equations for the neutrals and simplified magnetohydrodynamics for the plasmas. GTMR is primarily useful for mesoscale dynamics because it solves the full vertical momentum equation for resolution of acoustic waves and accurate representation of high-frequency gravity waves. You can see in Figure 5 the simultaneous propagation of acoustic and gravity wave perturbations in GTMR. Additionally, the newly developed local grid refinement feature allows for layered patches of increased resolution to be embedded and coupled together, and this not only saves on computational resources but also allows for more realistic specification of regional boundary conditions. The simulation using the results shown here is a 4-hour simulation of the first phase and uses a grid of 3 embedded layers where the innermost layer has a resolution of 0.1 by 0.1 degrees, which is about 10-kilometer resolution. Now to get to the results. Figure 7 shows the direct comparison of the GTMR extracted differential TEC and filtered observational TEC waveforms. These are the same as those shown in Figure 2. The left panel represents the simulation when driving the model using the direct propagation assumption, and the right panel shows the simulation when driving the model using the ground-coupled assumption. As you can see, each has its agreements and disagreements to the data. For the direct propagation assumption, the travel time and onset of the CVIDs seem to match pretty well. Additionally, the general magnitude distributions of the acoustic waves and gravity waves seem to be consistent with observations. The gravity wave packet does appear approximately 15 minutes off on some of the satellite receiver pairs, and most notably, the direct propagation is only characterized by a single acoustic gravity wave packet response. Focusing now on the ground-coupled propagation response, clearly noticeable are multiple wave packets, and the arrival and relative magnitude of the second wave packet is vastly improved in comparison to the direct propagation assumption. The initial acoustic wave packet is quite offset in terms of these, and the dominant modes don't produce the second wave packet envelope quite as well. The gravity wave packet does occur sooner in data and much smaller in magnitude, but overall the relative significance of gravity and acoustic dominance TEC perturbations as a function of distance from the source are reproduced. Focusing now on the spectral content, figure 8 shows the spectral content with a similar format to what was shown in the left panel of figure 2. The top panel here represents the observation, whereas the middle panel is the direct propagation simulation, and the bottom panel is the ground-coupled propagation. The spectral content for the DP settles to the near forcing frequency after first initially being quite good, whereas the GC spectral content seems to match much better to the observational data throughout the remainder of the time series. The gravity wave mode is present in the GC simulation, but much smaller. Focusing now on the phase speed computations, in the direct propagation assumption, the acoustic gravity waves have phase speeds of about 800 meters per second, and the gravity mode about 200 to 245 meters per second. These are pretty consistent with what is shown in the GNSS observations. The ground-coupled assumption does improve those phase speed calculations for the acoustic waves by increasing this phase speed, but also increases the gravity wave mode phase speed, which results in not as good as a comparison to the data.